force. The content contains two parts. Firstly, we review the forms and calculation of single-span beams. Then, let's review the relationship between loads and internal forces. There are three commonly used forms of single-span beams: simply supported beams, cantilever beams, and overhanging beams. For a planar member, there are three internal forces components: axial force, shear force, and bending moment. The axial force are considered to be positive when they make the beam in the tensile state. The shear forces are considered to be positive when they tend to make the portion rotate clockwise. On the contrary, the state is negative. We usually give sign in the axial force and shear force diagrams. The bending moment is positive if it causes compression in upper fibers and tension in lower fibers of a beam. But in structural mechanics, we don't need to give the sign convention. Just to draw the diagrams of bending moment at the tensile side, we usually use the method of sections to calculate internal forces. For example, we want to know the internal forces on section C. Firstly, we could determine the support reactions of the beam. According to sigma Fx is equal to 0, we could solve Fax is equal to 0. According to sigma Ma is equal to 0, we could solve Fb. According to sigma Fy is equal to 0, we could solve Fay. Secondly, use an imaginary section to cut the beam at the specified section C into two parts. We take part of the structure, such as AC part, as a free body to draw the free body diagram as this figure shown. Then determine the internal forces Fn, Fq, and M on section C according to the equations of equilibrium. In another way, we could solve internal forces directly. The axial force Fn is equal to sum of components parallel to the axis of all external loads and support reactions with opposite direction to the sum. The shear force Fq is equal to sum of components perpendicular to the axis of all external loads and support reactions with opposite direction to the sum. The bending moment M is equal to sum of moments about the centroid cross-section. Then let's review the relationship between loads and internal forces. Take a simply supported beam as an example. It is under the action of uniformly distributed load Qy in vertical direction and Qx in horizontal direction along its axis. Now, we take a differential segment dx as a free body. This figure shows the free body diagram. The internal forces on the left section are axial force Fn, shear force Fq, and bending moment M. On the right side, the internal forces are Fn plus dFn, the shear force Fq plus dFq, and the bending moment M plus dM. According to equilibrium equations, we obtain that Fn plus dFn plus dx times qx minus Fn is equal to 0. According to this equation, we could obtain that dFn over dx is equal to negative qx. According to equilibrium equation, sigma Fy is equal to 0, we could establish that Fq plus dFq plus Qy times dx minus Fq is equal to 0. According to this equation, we could obtain that dFq over dx is equal to negative Qy. For this section, according to sigma m is equal to 0, we could establish that m plus dm minus m plus qy times dx times half of dx minus fq times dx is equal to 0. We ignored this term, and according to this equation, we could obtain that dm over dx is equal to fq. These three equations are differential relationship between laws and internal forces. We could obtain regularity of Fq and M according to the differential relationship. The first case, if Qy is equal to 0, shear force diagram is a horizontal line and bending moment diagram is a diagonal line. For example, look at this cantilever beam under the action of a concentrated load at its end. We could draw its bending moment diagram. It's a diagonal line, upper side in tension, like this. And for this end, M is equal to FPL. Its shear force diagram is a horizontal line parallel to the axis of the member. That's positive Fp. We could obtain the value Fq according to the slope of the bending moment diagram. That's FPL over L. According to the differential relationship, the slope of the shear force diagram, dFq over dx, is equal to 0. So that's why the shear force diagram is a horizontal line. Another example. Look at this overhanging beam under the action of such a concentrated load Fp. Firstly, let's draw the beam's bending moment diagram. Look at CB part, no Q acting on it. The upper side of CB part is in tension due to the concentrated load Fp, so we could draw such a diagonal line. For the right side of the section C, its M is equal to Fp times half of L. Now let's take the section C and the support C together as a free body. According to the equilibrium equation of joint C, we could establish that the left side of section C's M is also equal to half of FPL. For section A, because it's a hinge, no moment is acting on it, so its M is equal to 0. We connect section A and C directly. That's the bending moment diagram. Because no Q is acting on the beam, so its shear force diagram is a horizontal line. According to the differential relationship, dm over dx is equal to Fq, we could find that for the CB part, the slope of bending moment diagram is half of FPL over half of L, so that's positive Fp. For the AC part, the bending moment diagram is such a diagonal line. The slope is equal to half of FPL over L. That's negative half FP. For the second case, if QY is a constant, shear force diagram is a diagonal line. Bending moment diagram is a parabola, and the convex direction is the same as the direction of Q. Look at an example. For this cantilever beam under the action of uniformly distributed load, here Q is a constant. We could draw its bending moment diagram. It's a parabola, and the upper side of the beam is in tension due to the Q's direction. So, could we draw such a parabola? Obviously, no, because the convex direction is the same as the direction of Q, so the parabola must be in this direction. And we could calculate these sections M is equal to half of QL squared. The shear force diagram for this cantilever beam must be a diagonal line, like this. For the free end, its shear force is equal to 0, and for this end, the shear force is equal to QL, positive. Another example, for such an overhanging beam under the action of uniformly distributed load, we could draw the bending moment diagram of CB part is also a parabola, upper side in tension, and we could calculate section C's M is equal to half of QL squared. For AC part, no Q, so its bending moment diagram is a diagonal line. Section A's M is equal to 0, so we connect these two sections directly by a straight line. Then, let's draw the shear force diagram. CB part, Q is a constant, so its shear force diagram is a diagonal line, positive. For section C's right side, FQ is equal to QL. For section B, FQ is equal to 0. AC part, its shear force diagram is a horizontal line. According to the slope of this bending moment diagram, that's half of QL squared over 2L. So the slope is equal to a quarter of QL, negative.